In this video, we are going to find positive integers m and n such that 85 to the power m minus n to the power 4 equals 4. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. First, I'm going to move the n to the power 4 to the right side. So 85 to the power m equals to n to the power 4 plus 4. Notice that n to the power 4 plus 4 is actually factorizable. In fact, I can rewrite that as n to the power 4 plus 4n squared plus 4 minus 4n squared, so that both expressions are equal, but now the first three terms can form perfect squared, and 4n squared is another perfect squared. So I can treat it as difference of squares and factorize it. Like this. And so we have n squared plus 2n plus 2 multiplied by n squared minus 2n plus 2. So now we can focus on this product. At this stage, there are two possibilities. The first is these expressions, n squared plus 2n plus 2 and n squared minus 2n plus 2 do not share any common prime factor. If so, then it's actually quite easy to solve. But what if these two expressions share common prime factors? Under this situation, because their product is a power of 85, then they can only share two prime factors, which are 5 and 17. So let's see what happens if they really have such kind of property. If 5 divides both n squared plus 2n plus 2 and n squared minus 2n plus 2, then by rewriting the two expressions into n plus 1 all squared plus 1 and n minus 1 all squared plus 1, we'll actually find out that for these two relations, they will give different outcomes on the remainder when n is divided by 5. For n plus 1 all squared plus 1, n can only be either 1 or 2 mod 5, while for the other case, n can only be 3 or 4 mod 5. So we actually cannot find certain number as the remainder when n is divided by 5, such that both relations can hold at the same time. So that means these two expressions cannot share the prime factor 5. Now what if they share the prime factor 17? We have n plus 1 all squared, I can say it's congruent to minus 1 mod 17, which can be replaced by 16 for the remainder. And so we can consider n plus 1 congruent to plus or minus 4 mod 17, and that means n is congruent to either 3 or minus 5 mod 17. While for the other case, using a similar argument, n minus 1 is congruent to plus or minus 4 mod 17, and so n congruent to minus 3 or 5 mod 17. Again, there is no overlapping case, so that means these two expressions cannot share prime factor 17 as well. Now from these calculations, we know that these two expressions cannot share any common prime factor, So there are only two ways that I can split 85 to the power m, and that is one of the expressions take all the factors, so that equals 85 to the power m, and the other expression equals 1. Or one of the expressions take all the factors of 17, and the other expression takes all the factors of 5. And because n plus 1 all squared plus 1 is clearly larger than n minus 1 all squared plus 1, so these are the only possibilities. The first one is easy to solve because for n minus 1 all squared plus 1 equals 1, then clearly n just equal to 1. But if I have n equals 1, the other expression will be equal to 5. But we are having 85 to the power m on the other side, so no solution for this case. Otherwise, we'll have n plus 1 all squared plus 1 equal to 17 to the power m, and n minus 1 all squared plus 1 equals 5 to the power m. To proceed, I'm going to write this as n plus 1 all squared plus 1 all divided by n minus 1 all squared plus 1, and that equals 17 over 5 to the power m. Notice that the fraction at the left side is actually not that large, as in the numerator is not really that much larger than the denominator, while for the right side we're having an integer power of 17 over 5, and that's 3.4, so it can grow really quickly. That means I can actually establish kind of some bound on the fraction at the left and try to reduce the number of possibilities for n. So I can say that the fraction at the left is at least 17 over 5, and we have a quadratic. And we have 12n squared minus 44n plus 24 is at most 0. And reducing the coefficients, we can factorize more quickly. And we have n to be between 2/3 and 3. And we know that n has to be a positive integer. So now we only have 3 cases to check. Which are 1, 2, or 3. When n equals 1, going back to our original equation, we have 85 to the power m minus 1 to the power 4 equals 4. Clearly not a solution. When n equals 2, we have 85 to the power m minus 16 equals 4. Again, not a solution. Finally, when n equals 3, we have 85 to the power m equals 85, and that means m equals 1. So that's a valid solution, and that means the only solution that we can have is that m equals 1 and n equals 3. So this is the final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.